Welcome. In this lecture, we are going to talk about top-down design methodology in digital voltage mode control. This is the continuation of the previous lecture. In this lecture, we are going to talk about top-down design method and then Verilog HDL coding for the overall digital voltage mode control. So, here again we will recall our digital voltage mode control implementation or the architecture that we have discussed. Then we are about to design that whole digital control module that we have discussed, and we have discussed that this is a main module and it consists of 3 sub module. One is the clock generation, the other is the digital PID controller, and the third one will be DPWM plus your dead time circuit. Okay. So, now let us start. So, this is the overall block which will look like this, internal architecture of this block. So, first we will start with the main module. So, again we start with the Verilog module and now the code will continue. So, first this is the name of the module which is the main module. So, I will say this is the main module, and when you go in the next week or the subsequent lecture, that is the step by step methodology of implementation and hardware demonstration, we will talk about this require a user constraint file, how to do, because we want to show using our actual Xilinx code, we want to show a live demo regarding that Verilog implementation in the subsequent lecture. But this is the main module. Today in this particular week, we are talking about how can we write Verilog code for this implementation, but while we will be demonstrating the live demo of digital voltage mode control, then we will say what are the other files are needed. So, there is a clock which we represent. So, this clock is nothing but this clock. Okay. Then we also need something like ADC clock, this is here. We are giving a DAC clock because we in our setup we have DAC. So, DAC clock you may or may not provide, or you may not use DAC data, because for voltage mode control you do not need D to A converter, but when you go to current mode we will use that. So, I am just keeping this particular line in mind. So, this is not used, I would say this is not used. So, we can drop this, we are not using this, not use here. We have just used because it is there, it exists, but we are not utilizing it. I will say not required, PWM high is the high side gate signal going to the driver, PWM low is the low side gate signal going to the driver, ADC data, that is the data coming from ADC, and this is a 10-bit data Q1.9 format we have discussed. DAC data we are sending 0 just to we may or may not send, because we do not need, because DAC we will not use in this voltage mode control. Q load is the going out, this is the Q load which is here, okay, and QLR tran which is actually here. That means, it is a input, what kind of transient you want, do you want a reference transient or load transient, we will discuss this. Now, we have to declare in the Verilog module which is the input, which is the output. Even among input, so clock is the input, QLR is the input, but these are the scalar input, sorry, scalar input, these are the scalar input. There are vector input also, 10-bit vector, and it is a sign, so we have to define the ADC data. The output we have clock ADC, clock DAC, PWM high, PWM low, Q low, there are so many output. We are sending ADC DAC clock that may or may not be needed, but output of the ADC that we are giving out, sending out data for the DAC, here we are not using it, but we can send some random data, unless it as long as it is not in the part of the loop, does not matter, but it is a vector 12-bit data, and remember it is a 12-bit offset binary that we will be using. offset binary, and this is 2s complement. Okay, and this also has like a plus minus 1 volt, but in offset binary, and this is also Q1.9 format. Okay. Next, this is a continuation, the code is continuing. So, we have declared the ports, all the ports, that means this part is called port declaration. Now, we are going to declaration of wire and register, because internally we are using some register or some wire, and we have already discussed about this. So, some of the register in out, because in out is a register, because this we are using for capturing the output data from the available ADC input, because we are taking data from ADC, and I told you that ADC data is coming at the rate of 25 megahertz rate. That means, but we need to get the output sample where we want, though it is sampled somewhat earlier, but we want to get the data sync, we want to load our register at some instant of time. Then we need to define the error voltage, that is why any error, and ncon, that is the controller output, is a 19-bit signed number. Then we are also defining FPWM, that is a, this is denoted as a local variable for frequency, switching frequency. It is not going out or coming in, but this is used for internally using as a switching frequency. So, all the gate signal will be generated with synchronized with this PWM, as well as the controller computation will happen at this with this clock, synchronized with the clock. We are using 3 Kp, Ki, Kd. So, Kp like a proportional control, Ki and Kd are integral and derivative controller gain in discrete domain, remember. And this we are defining as a parameter, which is a sign binary, 10-bit sign binary. So, when you say 10-bit sign binary, so it is a 10-bit, S indicates sign number and B indicate binary. Okay. And we are giving some value. What is the format you define? Q4.6. Then what is this value? This value will be, this corresponds to the 2 to the power 0 bit. So, it will be 1 plus, the first digit is 0.5, this is a 0.25, 0.25. So, you are using Kp is equal to 1.25. This is in the actual number, and we will discuss how to select Kp. Then we have a step down factor. So, we will take the design case study in the subsequent week, but here whatever value will come from the design, we can simply plug in here. The integral gain, again we are taking integral gain, and this is in the Q1.9 we have discussed. That means, Q1.9 means this will be 0.125. So, correspondingly you can get the value, you can convert this data. The derivative gain we are taking the first, all these 3 cases, the first MSB is 0, because it is a sign bit, we are talking about positive coefficient of the controller. So, all the bits will be 0, all cases the MSB will be 0. Then the other bit, if you see, it is approximately equal to 8. So, using Kd to be 8, but remember these are the controller value where there are other scaling factors. So, it is not actual, if whenever we did the MATLAB simulation, we have not considered the voltage feedback gain, current feedback gain, other factors. So, we have to consider. Now, we will bring back our MATLAB model again, and we will put those real scaling factors and want to simulate, and in the subsequent lecture we will see how does the simulation result, whether it is different from the experimental result or they are close. So, you want to discuss, but these are the values. Then once we have to also define, this is a parameter in rep nominal, this is a reference voltage, one is the nominal value, another is a delta. So, it is, you can say Vref nominal, corresponding voltage will come from this Q format, it is Q1.9 format, this is also Q1.9 format. So, you can get the analogous reference voltage in nominal. Similarly, this will give you delta Vref again in Q format. So, why do we need? Because you remember that in the Simulink we use a step command, right. So, here it is like a Vref to Vref plus delta Vref. When do you want? If you want to make a reference transient. So, this is possible that we can make a reference transient and we want to check the response. Okay. So, the actual reference, that means we are using a mux here, where this will be our Vref and this will be Vref plus delta Vref, the summing block 0 or 1 whatever, and this is, so this is like a nominal value. So, this is the actual Vref. So, the reference which is coming out, it is a mux of nominal value, nominal plus delta Vref. So, we can make a load reference transient, that is why we have used a wire variable. And so, nrep temper temp, what is the temporary value. So, we will go, these are for internal definition. Now, at the always at the switching frequency clock, that means whenever the switching frequency clock will come, this is my FSW clock, this age we are capturing the data coming out from the ADC, and this data we are talking about N out. That means N out is captured from ADC data, that means N out is basically the data coming of ADC data at some instant of time that is defined by the activity, the age of the FFW clock. That means it will only take, that means a clock synchronized operation. So, it will take the ADC data only at the age, rising age of the switching frequency clock. Now, we made some concatenation. So, we made some concatenation, we have where, so ADC data we know that what is the ADC data? It is Q1.9 format. That means it has total 10 bit, the first bit is a sign bit, all other bit, but we are capturing Q1.8 data first and padding with a 0. So, we are intentionally reducing the LSB and padding with 0, so that we want to decrease the resolution. Why it is needed? Because in digital voltage mode control, we need to make sure the resolution of the DPWM should be finer than the resolution of the ADC, and that is why we are discarding big, it is a 10 bit data. Okay, so that is why we are padding. Even if we want to lose 2 bit, then what we will do? We will do N out 2 bit. If you want to lose the concatenation, we will do ADC data. We are taking from 9 is the MSB to 2 and padding with 2 binary digit 0. That means 2 bits are 0. So, these are 2 bit number, binary number 0. So, padding with 0. So, that means we are losing 2 bit. So, these things are possible, and then once this is done, so this it will be a register, because it has to store the value and it will only take at the edge of this clock signal. So, that is why it is defined as a register variable here. In the previous example we have mentioned. So, this is a register variable. Okay. And error voltage is the reference minus N out. How are you getting reference? I am going to that point. So, we are now, this code is continuing. In fact, we may provide this full code in a 1 Word file or maybe a PDF file, because this is just breaking the code into, because in one slide it is difficult. So, clock generation circuit, clock generation. So, you have to give the instant name, the clock generator is a module name, and we also know that when you instantiate a module inside a module, we can instantiate at the module instantiation by name. So, that is why the dot are coming, where the actual clock generator module will have the variable input output port name f underscore clock, f ADC clock, and so on. We will go to that. And these are the local variable, because in the main module we are taking the switching frequency clock, the digital controller clock, which is this clock, the CLK. So, it is connecting. That means the clock generator taking this clock as the input and it is generating the output ADC clock, DAC clock, and the switching frequency clock, and this is the local variable. Then DPWM. the module name is this, instant name is this, and then again the dot means we are instantiating by name, and these names are consistent with the module input output variable name, and these are the local variable. Okay. So, for the digital PID controller, NER is the name of the input signal vector, which is the error. You are connecting with the error of this main module, local variable. Similarly, the controller output KP, KI, KD. So, this naming part we have already discussed in the I think previous week, where we have discussed in detail about the instantiation tile and all. Then we are also instantiating another module called DPWM underscore date time, because we discussed that we need to consider top down design methodology, where the main module will be broken into 3 pieces. It will create one sub module of clock generator, one sub module of PWM digital PID controller, another sub module of DPWM plus date time. So, this is the circuit, and it again takes one of the input as a high frequency clock, because this clock is needed to adjust the date time, because we can increase or resolution of the date time is defined by the high frequency clock, that is our 100 megahertz clock. So, we can change the number of clock unit with respect to this clock. That means, this clock time period is 10 nanosecond. So, we can change the date time in the order of 10 nanosecond, that means 10, 20, 30, but we cannot change it into 15 nanosecond, because the 5 resolution clock is not available. Okay. So, now creating event in the main module, we want to create transient event. So, we are giving 100 cycle, it can be 500, it can be 1000, it is a user defined. How it operates? So, first we have to define a counter is getting updated, then the transient register, okay, and the transient type, where again it is user defined, whether you want to define to be load transient or reference transient. And we can, in fact, we have given transient type from the external. So, when I will go to the live demo, I will show you a switch which can be placed either 0 or 1 position. If you set to 0, it will make load transient, if you set to 1, it will make reference transient. Okay. So, the transient type can be set from the outside, or you can define from inside. The only issue is the inside, because it takes time to compile the code and again load it to the target device. To avoid such kind of multiple time loading and the kind of compilation, we can simply provide an interface switch, so that you can change it and it will happen in real time. Then we are actually using a PWM clock edge, that means we are using the switching frequency clock edge, we are using this switching frequency clock edge, which is like this. So, this is my FSW clock. At the edge, we are incrementing, like a counter is incrementing like this. When a counter hit the half value of this, then the transient up to that point will be 0. That means, as long as, that means we are making like this kind of staircase, like up to full value. When it make hit, the transient type will be 0, then it will be 1, 0, 1, like that. And this is my Q tran, and this we are using for load transient. That means, I will show you, it can be load or reference. So, we will make 50 cycle one condition, another 50 cycle another condition. If it is a load transient, 50 cycle one load resistance, then another 50 cycle another load resistance with a combination. If we make a reference transient, 50 cycle Vref nominal, another 50 cycle Vref nominal plus delta Vref. Okay. So, this is the fine. So, Q0 or Q1. If it is this, else what will happen? Else it is continuing up to this point, when equal, all will be equal, will not update counter, counter will be reset, else we will do this to be 1, and then this n. So, you can make also n rep, that means we are just updating. Now, the load transient command which is going out, there is a Q load. Now, this Q load we are generating by muxing. this is my Q load 0 and 1. If it is 0, then it will take Q tran. What is Q tran? It is a resistor. So, Q tran means for 50 cycle it will be 0, 50 cycle it will be 1. So, that means Q load will make a load transient and there is a select line, we will come to that. The rest it will be 0. That means, if you set the select line which is a Q tran type, if this is set to 0, then it will make a load transient because the Q will depends on Q tran and which will change in half of this 50 cycle, like we have defined total cycle to be 100. So, first 50 cycle it will have 1 Q load will be 0, the remaining 50 cycle Q load will be 1 because it is connected to Q tran. But if this transient type, if this transient type is set to 1, then there will be no load transient, it will be connected to this point. But in that case will be, that means this is the comment of the data flow modeling of this mux. Similarly, here we are making n rep. So, n rep again we are making like this 0 and 1. So, 0 means it is your n ref nominal and 1 means we are getting this value plus there is a delta n ref and this is your n ref, and again the select line is Q tran type. So, if Q tran type is 0, the reference voltage will be fixed. If the Q tran type is 1, then actually there is another layer. So, here is another layer which is Q tran temp, that means it will be n ref temp. What is this? N ref 10, you can see for the 50 cycle it will be nominal value, the another 50 cycle you see for the first 50 cycle it will be, if you go back, the first 50 cycle it will take the nominal value, remaining 50 cycle it will take nominal plus delta n. So, this is a changing variable with respect to 50 cycle, but this is a fixed value. So, if Q tran type is set to 1, when the load transient will be 0, there is no load transient, but there will be a reference transient. So, this arrangement is made to make sure that switch is placed to see either load transient or reference transient. So, you can change, it is a user defined thing. So, you can change it. Then assign the DAC type, we are just sending 0 data, I mean this is we are not using any DAC. So, clock generator circuit. Now, we have instantiated this clock generator circuit, and this lecture we are only talking about clock generator because we have already discussed the DPWM dead time in the previous week. Okay. So, and we will be discussing digital PID controller in the subsequent lecture. So, here we will only talk about clock generator. So, what is clock generator? If you go inside, it takes input as a main clock which is a 100 megahertz clock and output as the ADC clock and DAC clock and switching frequency. It is just a counter. So, if you set this number to be 499, that means we are 100 megahertz clock, it is my F clock which is 100 megahertz, and I want switching frequency clock to be 200 kilohertz. Then what will be my NSW, which is nothing but F clock divided by FSW. So, it will be 500. I set to 499, why? Because it will count from 0 to 499. So, as a result total number will be 500. Similarly, I want ADC clock to be, let us say 25 megahertz. Then what will be N ADC? It will be F clock divided by F ADC, and that is 4. And I said 3 because it will vary from 0 to 3. That is it. So, you need 2 counter and you take the first clock, set it, I mean just for 10 cycle, then if it is equal to switching clock, that means we are making, suppose if this is your high frequency clock, let us say, so so if this number is 10, that means if this is your 10th number, this is your 10th cycle f clock. So my switching clock will remain high up to this, then it goes low, and if it is repeat. So here we are making like this. So this is your switching frequency clock. Now we can generate the ADC clock. So it will count from n ADC up to that. So it will first clock this, then next clock this, like this. This is a ADC, whereas this clock will be again this clock like this. Okay, maybe my drawing is not perfect, so you can try drawing. So or maybe we can erase this whole part. So first it will be high for one complete pulse, then 1, 2, 3, 4, again at 4th time it will be 1, and so on. So it will be divided by 4 clocks. So it is a clock division. So in summary, we have discussed the top down design method for digital voltage remote control, and we have also discussed Verilog HDL coding for overall digital voltage remote control. And in the next lecture, we are going to talk about digital voltage remote control, Verilog HDL implementation. That is it for today. Thank you very much.